right, this next example, example 4, determine the Maclaurin series of sine of x and its radius and interval of convergence. So for this one, we'll definitely use a table. So we'll start off. Far left column is n, starting with the value 0. Next column will be the nth derivative as a function of x. And then the next column will be that nth derivative evaluated at the center. And since this is a Maclaurin series, we know that our center value is 0. So our original function, the 0th derivative, is sine of x. And sine of 0 is, well, 0. N equals 1, the first derivative of sine is cosine. Cosine of 0 is 1. N equals 2, the derivative of cosine is negative sine. And then evaluated at 0 is again 0. N equals 3, the derivative of negative sine is negative cosine. Evaluated at 0 is negative 1. And then the fourth derivative here of sine will bring us right back to sine of x, in which case we just repeat. So we land right back up to here. So every 4 derivatives we cycle. So all the information just repeats itself. So we really only need 0 through 3. So we only need this information. Since the derivatives are eventually periodic. Okay. So because of that, our series is fairly easy to write down. So we know that for a Maclaurin series, it is the series from n equals 0 to infinity, the nth derivative at our center over n factorial x minus our center to the n, because it's the Taylor series, technically. So then if we make it a Maclaurin series, this becomes a 0 and a 0, in which case we could just write x to the n. There we go. So if we write this out, it's the original function. So I mean, these are the values we're going to use for this numerator. We're going to use 0, 1, 0, negative 1, repeat. 0, 1, 0, negative 1, repeat. So on and so forth. So if we write this out in its full, expanded form, this would be 0 over 0 factorial x to the 0 plus 1 over 1 factorial x to the first plus 0 over 2 factorial x to the 2 minus 1 over 3 factorial x cubed, and then we're right back to the start, which is 0 over 4 factorial x to the 4th plus 1 over 5 factorial x to the 5th plus 0 over 6 factorial x to the 6th plus, or minus, minus 1 over 7 factorial x to the 7th, and then I think we all get the idea. So now, we don't have to include these terms that are 0. We just don't have to write them at all. So because these whole terms are 0, we can just neglect them and not write them. So it looks like all the even terms vanished. So then what's left over here is 1 over 1 factorial x to the first minus 1 over 3 factorial x cubed minus 1 over 5 factorial x to the 5th. Plus this should have been plus 1 over 5 factorial. And then we have minus 1 over 7 factorial x to the 7th, so on and so forth. So our goal here would, there we go. We have it more or less done, just not written in this nice compact form. So how can we get it written in this nice compact form? Well, first thing we notice is that this series is alternating. So because it's alternating, we can use -1 raised to some power. Now, what we actually put inside of this power depends on whether or not we want to start with a negative or if our series starts with a positive. We start with a positive 1, so we should have some number that when we raise -1 to it, this minimum value, we get a positive number. Well, a negative multiplied by itself an even number of times would give us a positive 1. So we definitely want to start with an even number and then have it increase by 1 each time. So in general, we're starting off here at n equals 0, and 0 is an even number, so a natural choice here would be to use n to the -1. So we can build our series just by talking about it. So we'll do our series summation notation, n equals 0 to infinity. We'll have a -1 to the n. And our numerators are always 1 or -1. So we can treat this term right here as our numerators. And that takes care of that numerator, and it takes care of that alternating property. So now what about the denominators? Notice that we just have the odd factorials. So a nice little thing that is useful, especially when you're working with series and you're trying to come up with patterns or sequences, the definition of an even number, an integer, so a positive, negative, or 0 whole number, an integer is even if it is divisible by 2. So we can write any even number. So for instance, let's say if k is even, then we can express k as 2 times some other number n, where n is also an integer. Because 2 times any number, so this number n could be positive, or excuse me, this number n could be even or odd, positive, negative, whatever. That doesn't matter. So regardless of whether n is even or odd, 2 times n is certainly even, because 2n is clearly divisible by 2. So you can write a generic even number by just multiplying a generic whole number by 2. That result, 2 times that generic whole number, is guaranteed to be even. So what do you do to get a generic odd number? Well, odd numbers are just 1 away from every even number. So if 2n is even, then 2n plus 1 is odd. So if 2n is even, then 2n plus 1 is odd. Also, 2n minus 1 is odd. 2n plus 7 is also odd. So there's lots of ways you can do this. There's not just one way to write down a generic even or a generic odd, but generally speaking, 2n plus 1 or 2n minus 1, whichever one seems to make the formula look the nicest. Sometimes there are multiple different reasons why you might want to choose one of these various equivalent expressions for representing an odd number. So for us, we'll just use the simplest one, 2n plus 1. So I'll make this 2n plus 1 factorial. Now, since our series is starting off at 0, this is where it might be useful to think, do we want 2n minus 1, 2n plus 1, or 2n minus 3? All of those would give an odd number. So notice here, 2n plus 1, when we plug in n equals 0, this expression reduces to 1. So we do get the first term we want. If we had written 2n minus 1, substitution of this value 0 would give us 0 minus 1, which is -1, which is certainly odd, but that's not the number we have here. So 2n plus 1 is what works. Now, we're pretty much home free because we then notice that the exponent is exactly the same as the number that we are taking the factorial of. So since we already figured out this number can be represented by 2n plus 1, we'll just copy that expression down for the exponent. So there is our Maclaurin series for sine. So for us, this is going to be sine of x. Let's actually just write in some sine here. Okay. Now, what is the interval and radius of convergence? To do this, we will, of course, use the ratio test. So not a ton of room. I'll just do it right down here. Shouldn't need that much room. So rho is the limit as n goes to infinity, absolute a sub m plus 1 over a sub m. So a sub m plus 1 is negative 1 to the n plus 1, x to the 2 times n plus 1 all over 2 times n plus 1 factorial. Divided by a sub n, so this would be 2n plus 1 factorial. This would be x to the 2n plus 1, negative 1 to the n. Absolute values. So you got a little bit of simplification to do here. So the absolute values will essentially take care of our negative 1 to the n plus 1 and negative 1 to the n terms, because they're only positive 1 or negative 1, and then the absolute values would just make them all positive 1, so it's as if we can just drop them. So we'll drop them, and then we'll simplify these expressions here. So first thing to notice is 2 times n plus 1 is 2n plus 2 plus 1, which is 2n plus 3. So we want the same, we want to cancel the x's. So if this becomes an x to the 2n plus 3, and this x down here becomes x to the 2n plus 1, we want to get rid of the 2n plus 1s, so I can go ahead and write this x to the 2n plus 3. I can write this as x to the 2n plus 1 times x squared. And then the x to the 2n plus 1s would cancel. So we'll write this as 2n plus 1 times x squared. There we go. Our factorial, 2n plus 1 stays there. We'll do that. We'll have to do the same here, because this factorial just becomes 2n plus 3 factorial, which we can then, of course, write as 2n plus 3, 2n plus 2, and then 2n plus 1 factorial. So 2n plus 3, 2n plus 2, and 2n plus 1 factorial. And does that take care of everything? The negatives are gone, the x's are taken care of, and the factorials are taken care of. Okay, that works out. All right, after that, let's see, cancel the factorials, cancel the x to the 2n plus 1s. Now, the absolute values won't affect the x squared because, well, it's already positive, so nothing to worry about there. And then the bottom here, of course, we've got positive numbers, so it's as if we don't have any absolute values. So we have the limit as n goes to infinity of x squared all over 2n plus 3 times 2n plus 2. So this, of course, is 0. So rho is equal to 0. And since rho is equal to 0, this implies that we have convergence no matter what the x value is. So x can go as far away as it would like to from the center, and we still have convergence. Therefore, the radius of convergence is infinite. And whenever your radius of convergence is infinite, that means our interval of convergence is the entire real number line. So there we have our interval of convergence, the entire real number line, all real numbers. Our radius of convergence is infinity. And our Maclaurin series for sine is right there. Okay. Example 5. Determine the Maclaurin series of cosine of x and its radius and interval of convergence. Here we're going to use the term-by-term differentiation theorem. So the term-by-term differentiation theorem says if you have a power series that is absolutely convergent on some radius of convergence, with some radius of convergence r that's positive, then you can differentiate term by term, and the resulting series has the same radius of convergence. Not necessarily the same interval of convergence, because maybe that convergence or divergence at the endpoints changes, but the measure of the interval of convergence is the same. It's just those endpoints may be included or excluded. However, if your radius of convergence was infinity, then that means your interval of convergence before and after stays the same. It's all real numbers. So we really only have to worry about that interval of convergence slightly changing on the endpoints when our radius of convergence is some finite number, not infinity, like the case we have at hand. So first thing I would do is I would just say sine of x is equal to n equals 0 to infinity. We've got negative 1 to the n all over 2n plus 1 factorial x to the 2n plus 1. And we'll go ahead and say on all real numbers. So the radius of convergence is infinity. So this implies that cosine of x is the derivative of this series here. So the derivative would only affect this term. So here we'll have our negative 1 to the n over 2n plus 1 factorial. The derivative of x to the 2n plus 1 is 2n plus 1 times x to the 2n. And of course, we would have a little bit of cancellation here, because 2n plus 1 factorial is really just 2n plus 1 times 2n factorial, so that we can split off or break off one of the copies from the factorial, one of the terms, and cancel it with that term in the numerator. So this reduces to the sum from n equals 0 to infinity, negative 1 to the n, all over 2n factorial x to the 2n. And this is, it converges absolutely on all real numbers, so of course this really is saying that the radius of convergence is infinity. And this is I right here. What's interesting to note is that the power series for sine and cosine, look at the terms. Sine of x only has exponents that are odd, and cosine only has exponents that are even. This is another reason why we define, or we have used the name an odd function and an even function. Back when you first learned that in algebra, you might not have known exactly why we are using those terms. Why are we borrowing that term for whole numbers? Why are we using even and odd to describe the symmetries or an algebraic property of the functions? Well, one reason is that odd functions, in their power series, they only contain odd powers of x. An even function, its power series only contains even powers of x. So, just interesting to note.